Alright, so this is related rates part 2. So again, we're going to follow the same steps as we did before. Just different types of questions, but again, just looking at related rates. So we go to example 1 here, where it says topsoil is being poured from a truck at a rate of 2 cubic meters per second, forming a conical pile, so cone. The height of the pile is always 3 times the radius at the bottom. How fast is the height of the pile changing when the height is 2.5 meters? All right, so when I look at what we're looking for here, or what we have, the information, we're dealing with a cone. All right, now the first sentence here, it says topsoil is being poured from a truck at a rate of 2 cubic meters per second. So that is saying the rate of our volume is changing with respect to time at a rate of 2. So we know our dV dt. Now it says the height is always 3 times the radius at the bottom. Okay, so I always break it down. The height of the pile is always 3 times the radius. So our height, that means you would need 3 radiuses to get your height. That's the second sentence. Then we get to the last sentence. How fast is the height of the pile changing when the height is 2.5 meters? So we're looking for the rate of change of the height, so dH dt, when h is 2.5. All right, now, again with that formula sheet that I've posted in Google Classroom, so we're looking for a relationship that involves the volume and most likely the height and the radius of a cone. And I do have a formula, believe it or not, and the volume of a cone is equal to V equals 1/3 times pi r squared times h. All right, now in this formula, we are looking for dH dt, but we don't know anything about dr dt. It is changing as well, it looks like. But we do have a relationship here in which you need 3 radiuses to get you your height. And so what I'm going to do is substitute in for r, and so that I just have volume and h. Now, so to sub in for r, I'm going to have to divide this equation both sides by 3. And so r is actually going to be h divided by 3. All right, now I'm going to sub that into my equation here. So I get V equals 1/3 pi. That's just a number there. Now r squared, instead of r squared, I'm going to have h over 3 squared. And again, times the h that was left over there. All right, now to further simplify that a little bit, let's see here. I got 1/3 pi. All right, I square the h, I square the 3. So I'm going to have an h squared all over 9. All right, and then again times that h. Now I can further simplify that again. Let's see here. I got my denominators here. I got a 3 and a 9, so 3 times 9 is 27. So I'm going to have 1/27th. I still have this little pi hanging around. And then h squared times h is h cubed. All right, so now I'm ready to take the derivative. All right, again, but with respect to time. All right, so if I take the derivative of v with respect to time, well, I get dv dt. Now, I've got this constant out front, so I'm just going to write it down. So 1/27th over pi. All right, now I got to take the derivative of h cubed with respect to time. So I take the 3 comes down, times 3, times h, and then knock 1 off the exponent squared, but then times the derivative of the function inside, and we don't know that derivative, so I'm going to write it down, which is dH dt. All right, now it's time to substitute in. And let's see if we have enough information. We're looking for dH/dt. We know our h value, so that checks out. And we know our dV/dt value. There it is up there. All right, so we have all the information we need here. So let's see here. Time to plug in. So dV/dt was 2. Let's see here. Now I got this 3 here and a 27 here and a pi, so I might just figure that all out as a number there. So let's see here. I grab my calculator. I take 3 times it by pi, 3.14, and then I'm going to divide by 27. And I get to 2 decimal places. I get my 0.35. All right, now h squared. So then I have, well, let's go 2.5 squared. And then at the end there, I have my dH/dt. That's what we're trying to find out, the rate of change of the height. All right, now, further simplifying. So I got 2 is equal to, well, I'm going to figure out what 2.5 squared, do that first, then times it by 0.35, and to 2 decimal places I get 2.19, and again times dH/dt. Alright, and then my last step is to get, well, dH/dt by itself, so I'm going to divide both sides here by that 2.19. And what do you do to one side? I can do to the other here. And those divide each other out. And so my dH/dt, again, the rate at which my height is changing with respect to time. I'm just going to take 2 here and divide it by 2.19. And I get a positive 0.91. And again, our units, height was in meters and time was in seconds. And so, the height, to finish this off, is increasing because our rate is positive at a rate of 0.91 meters per second when h is equal to 2.5. Now, just a little side note on this one is that, say if the question asked at what rate is the radius changing? Well, in this case, this is where when I substituted in and replaced r, I would go the other way and substitute in for h and replace h in the equation. So I would use this equation and plug it in for h. And then our whole formula would then be in terms of r. So I'd have 1/3 pi r squared, and then h would be 3r. Well, that would have been a lot easier because then these 3's would have divided each other out. We'd have an r cubed. But again, that is if I was trying to find the rate at which the radius was changing. But this time it asked me for the height. All right, now next one here. A hose is pouring water into a large rectangular water tank with a square base, it's 3 by 3, and a height of 8 meters at a rate of 25 cubic centimeters per second. A small hole is draining water out at a rate of 5 cubic centimeters per second. At what rate is the height of the water changing when the height of the water is 3.5 centimeters? Okay, a lot to digest here. So we got a rectangular box. I'm going to draw that first. Again, bear with me here. I'm not much of an artist. Do my best. There's my rectangular box. All right, it's probably the best one I've drawn in a while. Now it's got a square base, so I'm going to call this x and that x, and then we're talking about height, so I might as well label that h. All right, now in terms, let's see here. So that is basically the first sentence, and it has a height of 8. Okay, good. Now it is being filled at a rate here of 25 cubic centimeters. So that means my dV/dt, let's draw that up here. My dV/dt, the rate at which my volume is changing, is actually 25 cubic centimeters. Except for, in my next sentence here, it says a small hole is draining water out of the tank. All right, well, if I have 25 coming in and a 5 going out, well, it looks like actually my rate is 20 cubic centimeters. Because again, we're losing 5 for every 25 we gain. Now, the last sentence. At what rate is the height of the water changing when the height of the water is 3.5 centimeters? So that means we're looking for dH dt. That's what the rate we're looking for when our height is 3.5. All right, so now I need a formula that involves volume, x's and h's. All right, and so, well, the volume of a rectangular box is length times width times height, which in this case would just be x squared. Here's my length times width, and then again, times my height. All right, now, here's something a little bit different. This is something we had last day that I can deal with right away, and it will save me a lot of issues, or not a lot of issues, but a lot of extra work. But the thing is here, but x is constant. The bottom of the box is never changing, or the base of the box is never changing. And so I'm going to sub in x equals 3 into my formula because it's constant. It does not change. Just like when we did our homework and we were talking about the kite flying away, where the vertical or the horizontal, or no, the vertical distance did not change. Or even the case with the ladder sliding down the wall. The ladder's length did not change. So we could have just substituted in, I believe it was 5 for the ladder length. But in this case, I'm just going to sub in right now. And so I'm going to have V equals, well, I guess we'll go with 3 squared times H. And so our volume is just going to equal 9 times H. All right, so now I can take the derivative of both sides with respect to t. So the derivative of the volume, the rate of change in the volume with respect to time, is the rate of the change of the volume with respect to time. And on this side, well, again, 9's a constant. And then take the derivative of h with respect to t. Well, that's just dh dt. All right, and so now I can sub in my numbers. All right, because I know dV dt, the volume is changing at a rate of 20, equals 9 times dH dt. All right, well, to solve for dH dt, I'm just going to divide both sides by 9. And so, well, dH dt is equal to 20 divided by 9, which is 2.22. And I believe our units, we were dealing with centimeters, and our time was in seconds. Yeah, so centimeters a second. And so a little therefore statement is that the height of the container, water tank, I should say, is again increasing because it's a positive rate there at a rate of 2.22 centimeters per second. Now I'm going to add this part in, but not necessary this time out, when h is equal to 2.5 meters. Now hopefully a few of you have wondered, hey, we didn't use that 2.5 meters, right? We had that value. We're looking for dH dt when h equals, what do I got there? Oh, 3.5 centimeters. Whoops. 3.5 centimeters. Maybe I was thinking of the last example. 3.5 centimeters. Not like it matters because this is a situation we had again. Why didn't I sub in h? Because it doesn't matter. Because this base of this box does not change, the rate at which the water level is going up is the same. It doesn't matter what the height. Whether you're at 1 centimeter or 4 centimeters, the height of it is still increasing at the same rate. So h It doesn't matter. It's not dependent on h. All right, next up, probably the toughest one we'll deal with right here. Go with the cone again. All right, so one of my favorite things. A large conical ice cream cone begins to melt, decreasing the volume at a rate of 1.5 cubic centimeters per second. Wouldn't happen to me, I eat it too fast. Now, if the radius is shrinking at a rate of 0.02 centimeters per second, find the rate at which the height is changing when the radius is 3 centimeters and the height is 1 centimeter. Okay, so here we go. First sentence. A large conical ice cream cone begins to melt, decreasing the volume at a rate of 1.5 cubic centimeters a second. So our volume is changing at a rate, it is decreasing, so I'm going to have a minus 1.5. All right, now it also says if the radius is shrinking at a rate. Okay, so that's my dr dt. And it is also negative because, again, it's shrinking. Now it says find the rate at which the height is changing. When the radius is 3, height is 1. All right, so we're looking for dh dt when r is equal to 3, h is equal to 1. All right, so again, we just went through this with the formula here for the volume of a cone, which again is V equals 1/3 pi r squared h. Now, here's where the difference is here. Not only do we not have a relationship between r and h that we can make a substitution, is that we got 3 different rates in which we know what's going on here. So I'm going to have to leave this equation just the way it is, which is a little bit different. And again, that's because we don't have a relationship between r and h. And, well, we know both their rates. And, well, we know 2 of the rates, and we're looking for a 3rd. But again, the reason is we don't have a relationship between r and h. So here's what I'm going to have to do. Essentially, I've got this, let's see, I got these constants out front. All right, which I'll probably just flip to a decimal. But then I have a function, r squared, times another function, h. And so I'm going to have to use the product rule when I take the derivative. Let's throw that in there. Because I have a function times a function. All right, so now here we go. I'm going to take the derivative. And so the derivative of v with respect to time, well, that's just dv dt. Nothing to it there. Now I'm going to take my, I'm going to simplify my 1/3 pi, because that's just a number. So I take 3.14 and divide it by 3, and I get 1.05. All right, now I'm going to take the derivative of the function inside the brackets there in the red brackets. And again, I have 2 functions, r squared times h, and that's why I'm taking the product rule, or using the product rule. And so the first thing is I got to take the derivative of r squared. All right, so that's going to be 2 times r times the derivative of r, which with respect to t, which is dr dt. And then I have times h, because it's the product rule. Then plus r squared times the derivative of h, which is, again, with respect to time, is dh dt. All right, so there we go. We've taken the derivative. Now, let's see. We're looking for, see if we got everything we need here. We're looking for dh dt. We have r, good. We have h, good. We have the dr dt, and we have r, and we have dv dt. Hey, we got everything. We don't have to find anything. All right, so I'm going to substitute everything in here. So let's see if I can go with big letters, see if that's going to work for me. All right, so dv dt, again, was negative 1.5 equals, I've got that 1.05 sitting there. let's go with the square brackets. 2 times r, and r was, let's see here, let's go up. R is 3. All right, r is 3. Dr dt is negative 0.02. And then don't forget I got that h there too here. H was just a 1. Good, that's not going to do too much. All right, plus r squared. So again, that is r is 3. So I'm going to have a 3 squared. And then we're trying to find dh dt. So I'm going to plug that in here in a second. Let's put it right here. dh dt, that's what we're looking for here. All right. Now, to simplify this thing, it's going to simplify real fast here, I think. So let's see. Again, I've got my negative 1.5 is equal to, I got my 1.05, which I'll worry about after. All right, so then I'm going to multiply 2 times 3 times negative 0.02 times 1. And I get negative 0.12. All right, plus, well, 3 squared is 9. And let's see, we'll go with the brackets here, dh dt. All right, so I simplified that up a bit. All right, now I'm just going to use the rainbow rule to multiply here, to expand this 1.05. All right, so we're getting down there now. It's getting easier. That's always the #1 thing in math. Things start getting more complicated, you know you're going the wrong way. All right, so let's see here. I got 1.05 times negative 0.12, and I get negative 0.13. Then 1.05 times 9 times dht, I'm getting 9.45 dht times dht. dht, I should say. All right, I'm going to move this over to the other side, this negative 0.13, so it becomes positive. And I can already tell you that's going to be negative 1.37 when I add that 0.13 over there. And that again is equal to 9 times 9.45 times dh dt. All right, and now I'm going to get divide both sides by 9.45 to get dh dt by itself. All right, and so dh dt is equal to negative 1.37 divided by 9.45, so it's going to be minus, and to 2 decimal places, I get 0.15 centimeters per second. And so in this case, given the situation, the height of the ice cream cone is decreasing, because our rate is negative, at a rate of 0.15 centimeters per second when r is equal to 3 centimeters and h is equal to 1 centimeter. And there we go. So again, that was probably the toughest one there. No doubt about it, because we had to use the product rule. But again, that's because there was no relationship between r and h.